We'll look into it someday.
Yeah, we'll look into it. Okay. So let me give you a little bit more. Let me just go one more step than that video did. There's like 11 videos in that series about imaginary numbers, by the way. We're not going to watch all of them. You don't have to watch any more of them if you don't want to. But they are kind of nifty. Let me give you one little thing. I'm going to talk about this now. I might bring it up a couple more times, but it's not 100%. You have to understand everything I'm about to say. When I say that, people kind of tune out, but shit. This makes so much more sense. Yes?
Are we entering 10.8 now?
We are in 10.8, yes. So yeah, let me ask you this. Oh, all right, before I bring that in. I've brought this up once before in the context of solving inequalities, and if you divide or multiply by negative, you got to flip the sign. Remember what I said about if I divide or multiply by negative, it changes the side of 0 you're on the number line? 1 is on this side, and then if I divide by a negative, now it's on that side. See how it's turning? I don't know, this is really interesting. I turn to get back here. So multiplying by a -1 is a half turn. You see what I mean by half turn? Isn't that 180 degrees? A full turn would be all the way back around. So if I multiply by -1, I go here. If I multiply by -1 again, I get back. I make a full turn. That's why two negatives make a positive. That's another reason why. That's why I like to explain negative is like telling somebody to turn around. And if I do another negative, turn back around, I'm like, well, that was fun. I'm back the way it was. That's why -3 is 3. Because -3 says 3, turn around. Now turn back around. All right, I'm 3 again. Does that make sense? Now, if I can do a 180-degree turn, I should really be able to do like a 90-degree turn. I should be able to do this kind of a turn. And this is where I don't know if you guys caught it, the reason they want to call it lateral numbers, at one point they kind of drew it, is because in reality, this is not the number line. This is the number line. This is the number line. This is the real part. This is the imaginary part. And again, we can call them lateral. I'd love to. But it's just not the way it's done. So
imaginary is always referred to as the x, or the y.
Yeah, imaginary is lateral to the x-axis. There's also an imaginary axis, a lateral to the y-axis. That's why they had to go 3D. See, remember when you picked it up and got all colorful? So the way you graph stuff in imaginary complex numbers is with colors. Because I'd actually need, I know I'm going really deep, I'd actually need 4 dimensions. How many dimensions do I have at the moment just for x? 2. How many dimensions does y have? 2 more. 4 dimensions. So we make color another dimension. So like anybody ever seen a topographical map? Like it tells you how high something is and low something is. They don't normally, sometimes they'll print it in 3D where it's bumpy, but normally it's just flat. Like if you look at Google Maps and ask it to do topographical, it'll just kind of make lines and make a different color. Color is the 3rd dimension that normally they want to pop out at you, but they can't make your screen become 3D. My screen is all bumpy. So they make it colors that show you the other dimension. So when you look up, like, if you look up complex graph, you're probably going to get a bunch of stuff that has colors on it. On my website, I've got, well, it's a fractal, really. I forget what I have up there. Let me see. It's not, oh, there it is. Yeah, this is a fractal. Well, let's look up, go to Google, images, complex graph. Give me some colorful ones. There's semi-colorful. Graph.
So is that why 3D glasses back in the day were like blue and red?
Oh, they just give me 2D shit. What's that?
So is that why back in the day, like the 3D glasses were blue and red because they're colors for the other dimension?
Well, that's got to do with messing with our eyes and how our eyes work.
It's like light
Yeah.
diffractions.
It makes us, the red one filtered out certain things that were just on the screen, and the green one filtered out, and then together they kind of made it look.
Oh.
Yeah, yeah. Now they obviously use different techniques because we don't need those same red and green glasses anymore, but we still need those other glasses. Anyways, there's some examples where the darker the color, the more imaginary the result was. So that's that color as another dimension. Okay, now, bring it back, bring it back, bring it back, bring it back. We're not going to have to graph this.
But people can graph that?
Of course. Now, these are obviously generated by computers, but you can graph it by hand in certain ways. Not very easy. We always definitely need a computer to get all the details, obviously, right? I don't have the time and patience to do this by hand. You could even,
That's pretty cool.
Yeah, I know.
All math is like that.
dude, that's the thing. Most of it is,
So
to
if
be
you're a
honest,
mathematician,
right?
you can be an artist.
We're just at the level where you can't see all of it. In fact, that me showing you that is not a part of this class. I'm showing you that just to show you where this goes. Right, and that's
What math
pretty.
is this?
That's pretty. But what's the equation behind it? That's a nice thing. I don't know if anybody would be curious. What is the equation behind these?
Is that
Yes.
the Mandelbrot theorem?
Mandelbrot is a certain type. There's a dude named Mandelbrot, and these are the kind of things he studied. I just wanted an image, and I knew that would give me the image I was looking for, because Google Images wasn't bringing me what I wanted. I'm curious, though, if they'll show you. Here's the Mandelbrot set. Yeah, here's the function that generates it. But if you want, anyway. Wee-haw, look at that. Yummy, yummy, yummy. All right, sorry. Math. Okay. All right, now here's the full thing. I'm going to bring it back, and I'm going to make it very clear what you need to worry about in this class. I'm getting some horrible stuff about how I go off on tangents, and I'm like, the tangents are important. They give you the more fuller picture. I will tell you what you need to be able to do for this class, but I will still go off on tangents every damn time I want to.
It is your right to do so.
Yeah, you can argue I've got a lot of rights. That would be counter to students, but I try not to do that. So here's what we call, so if multiplying by -1 is a 180-degree turn, then I need to multiply by half of -1, half of it multiplicatively, to go through. So if you really think about it just in terms of turning, multiplying by -1 is turning 180 degrees. Is everybody cool with what I just said? If I multiply by -1, I turn 180 degrees. Well, what if I only want to turn half of that? Well, then I got to multiply by half of -1, the square root of -1. 1 times the square root of -1 would be a 90-degree turn. And see how I already used the little letter I? That's the letter we use because, of course, they're called imaginary, unfortunately. So we define square root of -1 to be I. That's a definition. It's not something you can work out. Just like we define pi to be 3.141596, blah, 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 blah. I like it. So can somebody tell me, so if I do 2 of these, turns, I end up doing the same thing as if I multiplied by -1. And why does that make sense? Well, what's square root of -1 squared? What happens to the square and the square root? Cancel. So the answer is? That's the first type of number we've ever seen where when you square it, you get a negative result. That's why I kept saying, don't say it doesn't exist like the book does, unfortunately. It doesn't not exist. It's just not technically real. Now, like this video, it says, even though we call these imaginary, they're not imaginary. They're real things. They actually exist. It's just that that's the word that they chose centuries ago, or before they knew enough. Maybe. So what do we got here? I is the square root of -1 by definition. What's I squared? We just figured out what I squared is. -1. If If I keep multiplying by I can keep finding out higher. So what would I cubed be? It would be negative 1 times I. Is that cool? Do you guys see that? I cubed would be multiplied by one more I. So what's I cubed? What's negative 1 times I? Negative I. And look here, real quick, please. This is why I love this picture. If I do one turn of I, it's I. So I to the first is I. If I do another turn, I squared, it's negative 1. If I do one more turn, where do I end up? Negative I. So 3 turns, I'm in negative I. And if I turn one more time, where do I end up? Back to 1, because I to the fourth would be negative I times I. Negative I squared, what's I squared? Negative 1 is 1. So those are all the possible values that any power of I could have. What would I to the fifth be? It would be I to the fourth, 1 times I. It's I again. So let me give you a little shortcut. If you don't like the picture, let me give you a little shortcut about how to figure out any power of I. You have to know these. You have to start with these. And yes, these you must know. I to the first is I squared is negative 1, I cubed is negative I to the fourth is 1. What's I to the 0 power? What's anything to the 0 power?
0?
No, if I don't turn at all,
1.
1. So that's beautiful. It's another reason why a 0 power is 1, because that means you didn't turn anywhere. Now, I to the fifth would start over again, wouldn't it? Because you came back to where you started. So I to the fifth would be the same thing as I to the first. 4 goes into 5 once. I to the sixth would be the same thing as I squared. 4 goes into 6 once, remainder 2. It's all about the remainder is what I should say. 4 goes into 5 once, remainder 1. 4 goes into 6, remainder 2. So forth. Because every fourth one starts over again at 1. So watch this. What would I to the 12th be then? Well, this 4 goes into 12 evenly. It'd be one turn 4, another turn 8, another turn 12. So that's back to 1 again. Because 4 goes into 12 evenly. Remainder 0. 4 goes into, what about 23? 4 goes into 23, remainder 4 goes into 23. How many times? 5. Remainder 3. It's just going to have the same value as this. You guys, that's the shortcut. Instead of having to draw this picture every time and turn and do circles, you can just see what's the remainder. So if I say 23, haven't I done 5 total turns? Right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 20. And then 1, 2, 3. So I end up at negative I. Same thing as I cubed. So you must memorize these, and then you can figure out any other power you want to just by seeing what's the remainder when I divide by 4. So this is the same thing as I cubed, which is negative I. The most important power up there to remember, besides just the definition of I, is this guy. And I'll show you why here in a minute. That's huge, for one thing. It's the first thing I ever saw squared comes out to be negative. Okay. Okay. So let's do this. Let's start off with the easier stuff to do with these. Start off with the definition of what a complex number is. Complex number is just anything that is a real number plus an imaginary part. So for example, 7 plus 2i is a complex number. It's an imaginary number combined with the real number. everything we've ever seen before is a complex number. Like the number 6 is complex because it's 6 plus 0i. It's just that the imaginary part has a 0 coefficient. I like it. Okay, so how do I add these together? Thank the gods that that's relatively easy. Add and subtract. What would your gut tell you is true about this? I better not use the Roman letters for this. 4 plus 2i plus 6 minus 7i. What's your gut tell you is true here? Combine like terms. So what's the real part?
6 and 4.
Yep, so 10. And the imaginary part? Minus 5i. Sweet. So on the surface, it acts like a variable. In fact, I is a radical, and how do I add things with radicals? Well, I add the whole parts and I add the radical parts together, right? The like terms. Same idea. So 10 minus 5i. That kicks ass, thank God.
And that's it.
That's it for that. Yeah, that's it. So what about multiplying them? So you guys try the first few steps of this. 2 minus 3i times 5 plus 4i. It's trying to be 3. Anybody else not get their test back? So what do you guys get for this first step here again?
10
10.
plus 8i
Plus 8i, I like it.
minus 15i
Minus 15i.
plus negative 12i squared.
Yeah, minus 12i squared. Good. So on the first level of it, I acts like a variable, just like radicals did. Right? Radicals acted like variables to a point. And then I could do 10 8i minus 15i minus 7i. But here I could do something a little extra than normal. It's not just x squared, it's I squared. And what's I squared? I squared is negative 1. Now some people decide to just replace I with negative 1. Why the hell would I have to get negative 1 as symbol? Negative 1 is just negative 1. Square root of negative 1 is I, so I squared is negative 1. Leave this shit alone. Minus 12 times negative 1. So you get 10 minus 7i plus 12, so I get 22 minus 7i. The only thing up there that didn't look like I was a variable was I could replace I squared with what it is. Because I isn't really a variable, but it certainly acts like one. Combining like terms, multiplying them together, the power changes. I like it. Do this one here. See if any. Don't get overly optimistic. This is a little longer than you think. If you do a one step, probably did something wrong. This is not 1 cubed plus I cubed. Right? You gotta write that sucker 3 times. Foil out the first couple. Keep going. Jeff, you suck. I know I do. It's fine. That's why I became a math teacher. I suck. Okay, so this would be 1 plus I, 1 plus I, 1 plus I. Now, what's really funny to me is somebody tries to do all of that in one step, which is hilarious. You cannot, it's not possible. What's 2 times 5 times 7? How do you do that? Tell me the first thing you do. 2 times 5 times 7
Times 5.
is 10. Now think about it. Can you do 2 times 5 times 7 just directly? Can you? No, you cannot. You got to do 2 times 5 is 10, or you got to do 2 times 7 and then multiply by. You got to do 2 of them and figure out what that is, and then multiply the last one. You got to. You can memorize the answer if you're really feeling weird, but you can't work it out in one step. Same thing here. It's 3 numbers multiplying. So you got to pick a couple of them, figure out what that is. So what do you guys get for this?
I got 2 plus 4i plus
1 plus 2i, right? Plus I squared. This gets really weird. What's I squared? Negative 1 and 1 cancel. So you should just get 2i. And the I squared is negative 1, right? Negative 1 and 1 cancel. It's just the 2i that's left alive. Do you guys see that? Even if you made a mistake, do you see why the right way works? Okay, let me focus on that. Let me show every single little step. So here this would be 1 plus I plus I plus I squared. So this would be 1 plus 2i. What's I squared? Negative 1. 1 and negative 1 cancel, so you get 2i. All right. And then when you multiply this, it's just distribution. Is that cool? So you get 2i plus 2i squared. I squared is, so I get negative 2. Because I squared is negative 1. That's some freaky ass shit. Okay. Not too horribly. That's why I said, this is why I said I squared is negative 1 is the most important power to know, because it's the one that shows up the most. Now, I will give you a problem like I to the 91st. Tell me what that is, and you have to know all 4 values so you can figure out the remainder and figure out what the hell that is. That's great. But if you know I squared is negative 1 and you don't know this, I'm relatively happy. I squared is negative 1 is important. Okay. So now I want to point something out, and then we'll take a break, I think, maybe. You guys want to take a break?
Yep.
Yeah, for the rest of the day. So, like, couple things here. What's the square root of negative 9?
3i.
3i. Because how do I do this? Well, square root of 9 times the square root of negative 1, because I know the square root of 9 is 3, and square root of negative 1 by definition is I. So like the square root of negative 25 is 5i. The 25 I know is 5, and the negative becomes I, just by definition. Okay. So how would I do this? I will tell you this for sure, that is not positive 10. It's not the answer. You have to do each one separately. You can't multiply the insides. In fact, that only works when they are real numbers. It's just a shortcut for real numbers. What is the square root of negative 4? 2i. And what's the square root of negative 25?
5i.
5i. And what's 2i times 5i? 10i squared. I squared is negative 1, so you get negative 10. I like it. Which makes sense, because the square root of negative times square root of negative should come out negative. And then the other thing, real quick. What was the other thing, Jeff? There was one other thing. Shoot. I forget what it was now. Well, maybe that's a good place to take a break. Yeah. Let's take a break. Come back. 10 till.